Welcome to this CAST webinar. We're glad that you're here. We have a very great speaker today. We're pleased to host Dr. Faruque Hasan. He is the winner of the CAST Outstanding Young Researcher Award from this prior year, and he's agreed to give a presentation on his research. Let me go ahead and introduce Dr. Hasan. He is an associate professor at Texas A&M University. He received his Bachelor of Science in Chemical Engineering from Bangladesh University of Engineering and Technology in 2005, and a Ph.D. from the National University of Singapore in 2010. He also did postdoctoral training at Princeton University before joining Texas A&M in 2014. His research group develops fundamental process systems engineering and optimization methods for the design, intensification, and analysis of chemical processes, with applications to carbon capture, natural gas utilization, energy, the environment, and sustainability. Recent awards include the one that I just mentioned, the CAST Outstanding Young Researcher Award, the National Science Foundation Career Award in 2020, the I&ECR 2019 Class of Influential Researchers Award, the World Technology Network in Environmental Category 2018, and the Texas A&M Outstanding Achievement Award. We're pleased to have him present today on sustainable process synthesis and intensification of chemical enterprises. With that, I'd like to turn it over to Dr. Hasan. Thank you and welcome.
Thank you. Thank you for the very kind introduction, John. And I would like to also thank CAST Division for this award. I'm really excited to be talking to all of you about some of the recent research activities that has been going on in my group, especially in the areas of process synthesis and intensification. So what I'm going to talk today about, mostly the work has been done done by several PhD students, former and current PhD students, specifically Jianping Li and Emre Demirel, who graduated a couple of years ago, who started this work in the area of systematic process intensification and laid the foundation. And then current student Sadaf Munzur, who is continuing working in this area. So I'm really presenting the work that they have done today, taking this opportunity, and also want to acknowledge some of the funding sources that enable this work. Also, some key process systems engineering collaborators and colleagues that we have worked with and have guided us and suggested many of the work that we have looking into. So let me start with this big picture in mind. We have global challenges, for example, like the population, world population is increasing, and the projection right now is that by the end of this century, we'll probably have around close to 11 billion people on Earth. And because of that, and their improved quality, demand for improved quality of life, we'll see a significant increase in water, energy, and other chemical commodities. And to meet this increasing demand, of course, chemical engineering will play a key role. On the other hand, we need to also ensure the resources that are needed to meet this demand. And typically, right now, or over the last century or so, we have been depending on fossil fuels primarily to meet those demands for energy and associated chemicals. So now there is a challenge there too, because when we use conventional fossil fuels like coal, natural gas, or oil, there is an issue of emission, and as we all know, the anthropogenic CO2 emission is a concern. There is now a consensus through scientific studies and research that there is a relation between the global CO2 concentration in the atmosphere and global warming. And this is a concern that this is a challenge which is global. So to address this challenge, when we want to meet the demand for humankind, at the same time we want to meet the demand in a sustainable way, new challenges come in terms of how we develop new technologies, how can we make them more sustainable, and so on and so forth. How can we produce chemicals and plastics and polymers and many other chemicals in a more sustainable way. And so we have, as a global community, we also looked into unconventional feedstocks. For example, cleaner natural gas, which is a cleaner fossil fuel. There are other revolution in terms of, for example, shale gas, particularly in the US in recent times. And there are other resources which are more unconventional at a different scale. If we want to bring them, there are other challenges. If we want to bring them for using in terms of in the energy and chemical sector, one of the challenges there is that the separation cost for these unconventional feedstocks are significantly high. For example, in many of these unconventional feedstocks have CO2 as impurity, and to remove CO2, the cost is high. That's a challenge. Typically, we do not use these kind of unconventional feedstocks in a larger scale, and because of this high cost and issues around them. What we do typically, we kind of consider them as associated gas and burn them. And as you can see, that creates a secondary environmental problem, which is we now again produce more CO2 and put them in the atmosphere. There is another challenge apart from the cost for these unconventional feedstocks, which is many of these are distributed over geographic locations. They are sparsely distributed, and they are very small scale. So unlike centralized processing facilities, chemical and petrochemical complexes that use crude oil or energy resources in bulk, these energy resources are going to be at a small scale, and we need to decentralize our entire chemical enterprise. So that brings to the next challenge of how we can do that. When we think about small-scale manufacturing or distributed manufacturing, the key issue there is high cost. So I'm giving an example here in terms of producing hydrogen. So if we move from large-scale manufacturing of hydrogen to smaller scale, the cost can go up as high as 70%. And that makes many of these small-scale distributed manufacturing not competitive at the moment with their large-scale counterparts. So that's another challenge that we need to think about, that how can we reduce the intensity of capital investment for this kind of manufacturing per unit production. On top of this, we have to also address other challenges in terms of variability of these resources. These resources sometimes have changes over a day, or in terms of composition, in terms of their availability. For example, here I'm giving an example from landfill-based methane. If you look into the amount of methane that we typically get from a landfill, it is a variable over time. As the landfill is developed, we get more methane. But once this landfill is fully developed, then the amount of methane that we can get from this over the years would again decrease. So the question here is that how can we design a chemical process that will actually be able to use this kind of unconventional feedstocks from landfill, from biogas, from coal bed methane, or small scale shale and natural gas oil reservoirs. So these challenges really highlight or underline the fact that we might need a new process design and intensification methodologies. So the key question or underlying question that we address in our group is this, that given a set of feedstocks and given a set of targeted products with their specifications, what would be the best or what would be most suitable process configuration? Now, this depends on many targets, many objectives. For example, the design of a chemical process would be different if we change our objective from minimizing the cost to, let's say, minimizing the CO2 emissions. So having those targets and design objectives in mind, we want a general framework that can be applied to design more sustainable chemical process enterprises. Now, why is process design so important? If we look into the many different activities, many research domains of process systems engineering, we see that strategic planning at the top, where which is a long-term activity that is needed, that where we should have a chemical process, how much we should process, and so on and so forth. And then once we decide that, then we need to design the manufacturing facility, and that design involves both conceptual design and rigorous optimization. Once we have a chemical process design, then we construct them and then operate them, and that's where operational planning, scheduling, and real-time optimization come into. And of course, if we want to have a robust operation, process control or process safety are also very important. Now, if you look into these activities and try to see the impact on value creation, and there we see the value of design. The effort that we put for good design versus the value that we create has a high ratio. And as we go down from top to bottom, then cost increases, but with increasing cost, the incremental impact are not that significant. So at the design level, we have the highest impact on the value creation. The decisions that we make at the design level are critical because we cannot change them for many years once the plant is established, but it doesn't take that significant cost. So that's why design is important, because most of the decision making and their impact goes in at that phase. If you look into different pillars or different activities that we have typically in process design, first, one very important activity is conceptual design. I'm giving an example, very toy example here, that we consider different reactors, if there are reactions involved, and try to select a suitable reactor or set of reactor and a reaction network. And then, of course, we don't have 100% conversion, and that's why we need separation. Many different types of separations can be used, and we try to figure out what is the most suitable separation technique or a setup or a network of separation unit operations that we can use. So once we have these, we kind of come up with a configuration, which we call process flow diagram or PFD, for a given set of raw material and a product set. So that's kind of the norm and standard that we bring in people with expertise in relevant areas, designers, engineers, and then brainstorm to come up with a set of conceptual designs, and then try to improve upon them, then analyze those designs and try to find the best one. But that's not the only thing that can be done. We can also think of integration, process integration, because of course there will be some waste, so there will be some need for resources like energy, utility, water, and so on and so forth. So we want to try to have more sustainability in the picture by recycling, reusing some of the recovered resources to really minimize the waste and maximize our profitability. So process integration typically is considered after we have a set of conceptual designs. If you bring all these alternative ways of designing and integrating and put them together, then we go and try to screen in a systematic way the best process configuration. We call that activity as process synthesis. And given the advances that have been made over the several decades in terms of mathematical programming and optimization, we are very good as a PhD community to perform process synthesis. For example, here I'm again showing if we have a set of reactor alternatives, a set of separate alternatives, we really can apply, for example, mixed integer nonlinear programming or MINLP type of approach to really screen the best configuration for a process. Now, the last one that I want to discuss as a pillar of process design is process intensification. This is kind of a relatively new concept, but it's not just, but it has been there for some time in an ad hoc basis in most cases. So I'm giving an example of process intensification where it's a membrane reactor where we combine now this reaction and separation activities all together in a multifunctional unit operation, where the membrane separates the product as soon as that product is produced in the using catalyst. But these two phenomena occur simultaneously, and when there is a synergy between this reaction and separation, then we actually gain significantly higher productivity or higher PVD and less energy consumption. So that's why process intensification turns out to be a great tool or method or approach in process design. Many of us know the Le Chatelier's principle, for example, that if we immediately separate one of the product and byproduct, that moves the thermodynamic equilibrium to enhance productivity. This is one of the concepts for as an example that is used in process intensification activities to reduce the number of equipment, number of unit operations, and to reduce the investment cost, operating cost, and in many cases this leads to more sustainable chemical manufacturing. Now, typically the way we consider these different activities is that we have first perform process design at the conceptual level, then we perform process integration and synthesis, and maybe then think about novel ways of intensification. But along the way we might miss many non-intuitive solutions, and that's one of the focus of this talk, that how can we systematize and bring all these activities together in a systematic framework so that we do not miss those non-intuitive solution alternatives. Now, there has been recent work, for example, from Professor Balde in 2015, who showed that intensification is actually can be considered as an extreme case of integration. So, which kind of tells that all the activities that we have, all the methods that we have developed over the years in terms of design, integration, and synthesis can be extended towards process intensification using computer-aided methods. One other thing I want to highlight here is that along the design activities, we always look for innovative design methods. It's an emergent property when we combine these activities. But one key question there is that how can we systematize innovation when we do process design? Well, how can we come up with new equipment designs which previously have not been considered? A bit more on the process intensification. There have been many different definitions, but one thing is clear that in process intensification, we look for drastic improvement over incremental improvement. Here I'm giving an example of a drastic improvement, which is a classic example from Eastman Chemical methyl acetate process, where before intensification, the same process uses many different separation in distillation and columns and others. Once we look into the synergistic phenomena in this chemical process, then one can think of a single multifunctional equipment that can achieve the same performance that a large complex chemical process can, and all the activities can be merged into a single task integrated column that I'm showing on the right hand side, which not only reduces the number of equipment, but also it reduces the operating and capital investment, so operating costs and capital investment. So there is a win-win situation in terms of process intensification if we do it carefully. But the key question here is that whether this kind of intensification is always applicable. Can we do it for any kind of chemical processes? If not, then what will be the design rules and recipes that are applicable for applying synergistic process intensification? There are other examples of intensification. For example, dividing wall column is a great example where we can separate a multi-component mixture of more than 2 components using a single column, which reduces significantly the investment cost of a separation network. We can have reaction and distillation together in a reactive distillation setup. That's a form of intensification. As I mentioned earlier, membrane reactor is another example of intensification. Sorption enhanced reaction processes where we use heterogeneous solid catalyst and solid sorbent. The catalyst converts a raw material into a product or set of product, and then the sorbent immediately adsorbs one of the products by then pushing the thermodynamic equilibrium for further enhancing productivity. So all these are examples of intensification, but given a new design problem, it is not always obvious that what type of intensification is the most suitable. So that is a key question that we want to address, we address in our group. Naturally, there has been a lot of interest in process intensification activities. In collaboration with Professor Pistikopoulos' group at Texas A&M, we studied the recent development a few years ago, and we saw that there has been a significant interest both in the areas of developing many different process intensification technologies, as well in the academia. The number of academic papers have increased significantly over the years, and also in number of patents, as I'm showing in the right side, in different PI techniques are also increasing. So all these show there has been a significant interest in this area. There are other recent reviews, excellent reviews from Professor Murray Aden and Professor Gunny's group and Professor Grossman's group. All these are really great reviews that talks about different challenges and opportunities in process intensification. In our group, we try to address a couple of questions. In the synthesis part, the question that we address is that how can we really systematically discover new intensified processes without spending a significant amount of time and effort, without doing exhaustive screening. That's one thing. In terms of identification, we look into this question of how can we systematically identify pathways that would naturally lead to intensified design. So the synthesis, while process synthesis addresses a greenfield type of design, or a new design, identification addresses the process intensification questions for existing designs. So if you're given an existing process flow diagram and you want to improve that without making minimal or too many changes, or under budget constraints, how we can improve a process in terms of sustainability or economics. That's the question we address in the identification part. And of course, there is analysis. For example, we look into some theoretical questions that under which conditions intensification is desirable. And if I have time, I'll discuss about how actually it's not always desirable to have intensification. In many cases, it may not lead to improved processes. So in that case, the question is, can we classify those kind of designs versus synergistic designs? Now, all these activities depend on a fundamental question, that can we have a representation of chemical processes that will allow us to do systematic synthesis, identification, and analysis. There have been many different representation techniques, as we all know. For example, superstructure-based process synthesis and intensification use superstructures that bring all together all possible ways of combining and configuring unit operations in a single large process flow diagram. But the challenge there is that when we think about intensification, many times we will miss novel intensification just because we did not think of that unit operation and consider them in our superstructure. So what we need is kind of move from unit operation based representation towards a more phenomena or function-based representation. And recent work from many different groups have shown the benefits of that bottom-up approach of phenomena-based representation, which allows computer-aided process intensification more suitable for this kind of activity. So in our group, we have proposed this representation using building blocks. And let me take a couple of minutes to describe what I mean by this building block-based approach. Let's consider an abstract block here. If I consider flow to the block and from the block, then we can perform mass balance, energy balance for this block. So this building block is kind of an abstract representation of some volume in a reactor or in a separator or any general unit operation. If I assign a catalyst to this block, then this will become a part of a reactor. If I assign a solvent to this block, then it will become a part of an absorption column, and so on and so forth. So that's how we can, consider a general building block and then use this building block to represent many different unit operations. We can consider feed comes in or product withdraw, then that will allow us to create many different mixers, many different separators through using this kind of building block notion. We can assign a temperature, a pressure, and composition. Once we do that, then we can model this building block using rigorous thermodynamic approaches of thermodynamic packages. So that will tell us what happens when there is a mixture present, what will be the resultant composition, what will be the temperature, what will be the pressure when we mix and or when we separate things. Now, if we bring a set of building blocks together, then it becomes more interesting because then we can represent even more set of classical unit operations. To do that, we consider not only the interior of the building block, but also the boundaries of the building block. So we have three different types of boundaries that we typically consider in our building block-based approach. One is the unrestricted boundary, which means that if I have a pair of blocks from here I'm showing from center and the top, if the boundary between these two blocks is unrestricted, then the temperature, the pressure, the composition of these two blocks will remain the same. In other words, it will represent nothing but a pipe, for example. But if I have a second type of boundary, which is completely restricted boundary, then it will not allow any mass to flow from, let's say in this case, from left block to the center block, but there can be still heat transfer happening. So this will allow us to, represent many different heat exchangers, for example, when we design a chemical process. The third set of the boundary that we consider, we call them semi-restricted boundary. And this is very important for representing chemical separations. For example, if I have a pair of blocks in the center and the right, if I assign a membrane, then I can selectively allow one chemical species over others to flow from the center to the right. So these two blocks together then represents a membrane separator. And if I bring more and more of this pair of membrane separators, then together it kind of will represent a membrane module. So these set of building blocks and three sets of boundary definitions are actually the key design elements that we consider in building block-based representation. I'm just going to give an example. So if I assign some small examples of how this would work, if I assign a catalyst in a single block, that will represent a CSTR. But if I bring a set of building blocks with the same catalyst, then it will represent a plug flow reactor. And we have seen that as we increase the number of building blocks, then this representation actually matches the performance of actual plug flow reactor. We have in silico validated that approach. So that gives us a confidence in terms of that, yes, building block based representation can be applied to represent many different unit operations and many different classes of reactors. In terms of separators, here, as I mentioned earlier, that a pair or two building blocks with a common boundary, which is a semi-restricted boundary with a membrane material, will represent a membrane separator. But if I bring this pair again and again in a sequential form, that will represent a large membrane module. So to represent a membrane module, we do not need a new unit operation. This setup, the collection of the same building blocks and assignment of the boundaries will do the job. And we have applied these technique again even for intensified membrane reactor representation. So if one of the sides, let's say the permeate or the retentive side, has a catalyst block, then this whole setup becomes a membrane reactor. In terms of vapor-liquid equilibrium, we can represent a flash separator using two blocks with a semi-restricted boundary in between, which represents the vapor-liquid equilibrium phenomena. If we bring them all together, then this becomes a distillation column with many different building blocks. One type of block would be the liquid phase, another type of will represent the vapor phase, and there at the interface we apply the thermodynamic equilibrium. So that kind of leads to even more complex or complicated configuration. So we can use this building block representation to even represent the Eastman chemical task integrated column that I showed earlier. So, and we have also validated this approach that building block-based approach, if we use many different sets, then it approaches the same performance of a rigorous reactive distillation column. So the point here is that we can use the same notion of building block and boundaries to then reorganize them to create many different unit operations in the same framework. So to summarize, let's consider a set of building blocks. If we bring them together, they can represent many different phenomena, and many different phenomena can then represent many different unit operations, process units, and a collection of process units becomes a process flow sheet, and many different alternative process flow sheets will give us a superstructure. So that way, we now have a single representation of a superstructure just in terms of building blocks and boundaries. So this kind of tells us that, yes, there is a possibility of a generalized representation of process superstructures, rather than spending significant time and effort in terms of problem-specific superstructure. We can have a common superstructure for all design problems. And the way it would work is that we have a superstructure representation. You select a set of those, a subset that kind of represents an unit operations, for example, a membrane separator or a membrane reactor or a dividing wall column distillation or even task integrated column. So all these unit operations are kind of embedded in the same superstructure. Even we can expand that to an entire large-scale process flow sheet. Here I'm showing a classical representation of a chemical process flow sheet on top, and the equivalent building block-based representation on the bottom. And so which says that once we have this building block-based representation, we can then perform process synthesis on the building block-based representation, which is much easier using mixed integer linear type or linear program type of formulation. And we can optimize over that. And then we come up with a new organization or rearrangement of this building block, which represents a better process flow sheet. And we can then convert that building block to the classical representation, with which then have better annual profit or better return on investment. So we have done this exercise and combined all of them together in a general framework, which we call SPICE. SPICE stands for Synthesis and Process Intensification Chemical Enterprises. The SPICE includes this building block representation that I mentioned. It includes thermodynamic property models. It includes all these mass and energy conservation laws and phenomena models, so that we can now perform process design activities for many different problems. So the user can come up with a different set of feedstock specification, product specification, and design targets. They can also pick different materials like catalysts or separators or solvents or membranes that they want to test. They can also select goals of different levels of goals in terms of techno-economic and life cycle analysis, and they can even bring their own phenomena or unit operation models, which then we can include in SPICE, and the SPICE will then tell, okay, for a given design problem, whether it is more useful to intensify or not. It can also give us different designs of intensified process unit operations with their cost, with their energy consumption and emission specifications. SPICE can create new process flow sheets and screen over different process flow sheets. It can also even connect different material properties with process performance to provide a map of process performance versus material properties to guide experimental synthesis of different materials. This is a busy slide. I'm just going to skip this for the sake of time. But the idea here is that we have a general mixed MI and LP formulation representing mass and energy conservation laws and different process configuration and constraints, and also different phenomena models that are embedded together in the MI&LP model of SPICE, which we then solve it using commercial solvers like Antigone or Baron to find global optimal solutions on these design problems. So quickly, just to show some example problems that we have worked on. So one of them here is this ethylene glycol or EG production process. And so the user comes with this specification of the feeds and the reaction that they want to consider, and the product specifications in terms of the purity and the amount that they want to produce. So that's kind of the user input to the system of SPICE. And then SPICE generates different process flow sheets. For example, one of them is shown here, where if the user doesn't want intensification, then SPICE will generate this non-intensified process flow sheet with all these specifications. So it is a systematic way of generating process flow sheets without spending significant time. If the user wants an intensified process flow sheet, SPICE can generate that for that also. And here we see that for this particular example, process intensification is actually a better approach for this problem, where we have designs that has less number of equipment and less investment cost. So this is one example. Another example here, I'm showing that if this now user wants to consider multiple objectives, one is maximizing the return on investment versus the other one is minimizing the total CO2 emissions for sustainable design, SPICE can then generate a set of design alternatives and provide the return on investment and emission value for all of them. For example, here I'm showing is that for reactive distillation type of intensification, what would be the return on investment versus the emission, versus if I do not consider any intensification, but consider this PFR distillation recycle classical design approach. And here we see that actually the non-intensification version of design is better in terms of return on investment. So we can also generate more different alternatives by running SPICE over and over again using integer cuts to create different alternatives. And we see that there exist many different alternative ways of processing and producing ethylene glycol with different ROI and emission values. So this is a map that we want to generate by using SPICE. And then at the end of the day, it goes back to the user to decide which design they want to actually implement. So with that, let me quickly summarize what we have been working on in this area. That intensification has a lot of potential for addressing many of these challenges, including the global challenges, that how can we design new chemical processes which are more sustainable, which uses less energy, and have less CO2 emissions and other emissions, less waste. We have analyzed different approaches in P.Sc that can do this, but we think that process intensification can help in that activity, but we really need a general representation that can bring these different pillars of design all together in a general framework, single framework. To do that, we have proposed a building block-based approach, and we believe that this is a step forward towards designing new chemical processes, which for the next generation of chemical manufacturing, and which can bring significant benefits to the designers. But there exist many different challenges, of course. For example, we are yet to discover the fact that design rules that can be applied for just looking at a problem and say that, okay, intensification may not be applied here because there is no synergy. How we analyze those kind of synergy in a more mathematical form, in a more systematic way. So that's kind of an outstanding question. How can we, systematize innovation without even postulating new design alternatives and discover those? That's another outstanding question. So with that, let me stop here, and I would be happy to answer the questions. I hope there is some time. So back to John.
Fantastic. Well, thank you so much, Faruque. That was a very motivating presentation and many new ideas that your group is working on. I even noticed you have somewhat flavors of SPICE as well, like the Mars, the membrane-assisted reactive separations, and other parts that are attracting a lot of attention right now because of how they're being able to be used for designing these systems. Well, that's great. Thank you for that. We're going to open it up now for questions from the audience. And just to get started, I have a question here. Go ahead and put the question into the chat window, or if you'd like to unmute and ask a question as well, just put the little raise hand sign. I'll know that you have a question, or you can just unmute. I had just one question here. These look like very large scale mixed integer optimization problems, especially as you grow the number of blocks and the number of decisions that you can have. Can you say anything about how this scales with complexity?
Yeah, so yes, absolutely. As we increase the number of building blocks, so there is this trade-off between the accuracy of these models versus the size and the complexity, right? And so, and that's till now is kind of more of an art in our group than coming up with the systematic framework. But we are actually looking into that by posing some questions. For example, what is the minimum number of blocks that are needed to represent a design problem with certain accuracy without increasing the size? So that's a question that can be addressed in terms of, okay, how many what is the minimum number of blocks that are needed to represent a reaction, a set of reactions, a set of separation phenomena. So that way we can formalize that for a given design problem, let's start with this number of building blocks. And of course, we can always increase that to approach a more accurate solutions. So that brings to the next question, that in the algorithmic side, what can we do to make this solution more efficient? So we're looking into the spatial structure of this problem. Of course, this trade-off that we bring in more phenomena, more number of blocks and boundaries, the assignment becomes more complex. It's a combinatorial problem in that side. And of course, we also have non-convexity in mass and energy balances. So to address that, what we're really hoping for is that we analyze this general form or the special form of building block-based representation, because you can really decompose this problem into a subset of building blocks and then try to solve them separately in parallel and then bring them together. So that's one approach that we are looking into. But if someone wants to solve this as a single optimization problem, yes, this is a challenge which is outstanding. That many times, if we use, for example, global solvers, it takes either a long time to solve, or it does not close the gap. Really, the challenge there is solving the relaxation problems with tighter bounds and improving that bound. So that's something that we're actively looking into. But I also want to mention something that we are addressing a design problem. We can take time. If we can come up with a solution which is really more sustainable and more useful, we can take even days, we can take even months. Once the solution is there, it's really going to make an impact. Unlike many other problems like real-time optimization or control, which needs to be solved instantaneously, we do not, we have that luxury at least that we can spend some time. So I think this really points to the trade-off, which we have probably more options to exploit heuristics and previous design rules that really expedite our solution approaches. So it was a long answer, but yeah, that's a good question.
Okay, we have some time for some additional questions. Okay, Mario, go ahead.
Thanks for your presentation, Faruque, and congratulations again on your award, very richly deserved. I had a question. One of them you already touched on, which was related to how you could potentially quantify the dynamic aspects of some of these designs, if there are, rule-based techniques that could be used to help, pre-screen some of these designs. So you kind of touched on that already. The other question I wanted to ask was, in a lot of the options that you considered in the examples you showed, there was a need for solvents, mass separating agents, and so on. Could you incorporate, or could you envision in the future a extension of SPICE that maybe simultaneously solved the design of these materials, whether it's, molecular design or anything like that? Because the representation lends itself to a group contribution type approach for doing, solvent designs as part of that assessment. So is that something that you could envision happening in the future?
Yeah, thanks, Mario, for great questions. So I'll probably touch up on the second one. And of course, you have been working in this area for a long time, and I really appreciate that bringing in. So SPICE right now, we look into more of the unit operational representation at the lower level. But you're absolutely right. Our designs are as good as our materials that we consider, right? So here is probably there is an opportunity to bring in group contribution methods to extend this approach rather than coming from a given material, find the best design. We want to pose this question that, okay, let's do this simultaneously in terms of discovering new processes and also the best material, either screening or maybe finding new solvents as well. But of course, that will again increase the complexity of the problem significantly, which the way we are thinking right now is that this bringing this process material mapping. So we can postulate a hypothetical catalyst or a hypothetical solvent with all these fundamental thermodynamic relationship there, and say that, okay, let's design a process considering there exists the best material, but what would be that property? For example, if what is the best selectivity and permeability if we need a membrane, and if that relationship is already there, then probably we can complement to our material scientist colleagues that, okay, we are actually looking for this selectivity and this permeability, not the best selectivity, because that is not always the case. We have already seen that the optimal process does not consider always the star materials, right? So, and that's probably the first step, and then group contribution will really lead to what will be the structure of that material, right? So right now we're looking into process performance and the material function, and then function to the structure rather than coming from structure, function, process. So that is one way that definitely look into. But yeah, thanks for the suggestion. We haven't worked on that yet, but yeah, I think that could be a great avenue to look into. The first question you have in terms of the dynamics. Again, what I have shown is mostly the steady state problems that we are solving, right? But many of this intensification actually happens when we exploit the dynamics or the kinetics of a process. And there, the real question is, when we bring multiple phenomena, are those the kinetic and the dynamic response of those phenomena are considerably similar? If we don't have similar dynamics, then it is probably not going to be synergistic. So we are posing that question from the synergy analysis of synergy performance. What is the static synergy versus what is the dynamic synergy? If both are there, then we will have intensification at both levels.
Thank you. Just a quick follow-on comment, Faruque, for the on the molecular design side. One thing that you can do, which is kind of what you alluded to, if you solve the complex problem on the process side in terms of the desired properties you want a solvent or whatever to have, that actually allows you to decouple that additional complexity and just afterwards solve a molecular design problem that matches those. So that would be one way of kind of handling that level of increased complexity. And I like the analogy you used for the dynamic response. The first thing you're doing is finding out if the best case process under steady state condition is attractive, because if it isn't, then let's not worry about the dynamics, right? I mean, that's really the first step. So thank you, and thanks again for your presentation.
Thank you, Mario. You really summarized this really well, and thank you.
Okay, very good. Any last questions? Okay, well, fantastic. Well, thank you. And with that, we'll go ahead and conclude this presentation, and really appreciate Professor Hasan and for his presentation. And again, congratulations on the award.
Thank you so much.